Okay, so let's get started today. Okay, so what we're going to do is we're going to recap exactly where we were last time first, which is we had laid out the framework of general relativity. Okay, and the framework had a couple of things in it. It had basically the requirement that space-time is a manifold. We don't know what that manifold is, but you assume that there's some manifold. Okay, so whatever the topological structure is, there is something. The laws of physics have to take the same form in all coordinate systems, okay, or the laws should be phrased in such a way that they are coordinate invariant. Okay, so they should only depend on coordinate invariant things. And in other words, that the laws are invariant under diffeomorphisms on that manifold. Okay. And the third principle was that the manifold has a 0-2 metric tensor G on it. Okay, and this metric tensor is the new version of what we were previously thinking of as the gravitational field. And equations that govern particles or fields, they involve a metric compatible torsion-free affine connection, that derivative that we had defined earlier, which uses parallel transport defined in such a way to be metric compatible. Okay, metric compatible, of course, being this should be true. Okay, this should be 0. Okay, for any ABC. And within this framework, we built some laws. Okay, and the laws, I told you what their form was, but I didn't argue why it should be in this form. Okay, again, you can't really prove that the laws are this form. You're trying to write down the most general laws which are compatible with the principles that we've outlined. Okay, so the first principle was something like, I didn't write it clearly last time. It was m times delta u, where u is the force velocity of a particle, is equal to f, where f is the force acting on the particle. And this was the left-hand side is a vector, okay, a vector defined at the location of each particle. And f is a force, okay, which you can think of as due to some field, but this is due to non-gravitational forces. Okay, and this is also a vector. Okay, and this is a vector in the generalized sense of a vector. Remember last time I told you that you can always think about, let's say, a direction, right, in space like this and say that this is a vector. But this notion of a direction in space as being a vector is very specific to flat space, defining this as a vector. Okay, the more general way to define vectors on arbitrary manifolds, that was the entire process that we went through of deriving them through derivatives. Okay, that is a more generic way to define vectors, which is valid on arbitrary manifolds. Okay, not necessarily flat space. So so this idea of a vector, okay, or equating vectors, this idea was, there's something even more powerful about it. It was coordinate independent and metric independent. Okay. Okay, the next equation that we saw is, so this equation is sort of the analog of f is equal to ma. Okay, it's the upgraded version of that to be compatible with all these principles that we wrote down. Okay, the next rule is an analog of Poisson's equation. Okay, so it's the upgraded version of this equation. And on the left-hand side, we have the Einstein tensor, which, if you'll recall, was some combination of the Ricci tensor and the Ricci scalar. So it's made up of some curvature-dependent quantities. And the right-hand side was, it has Newton's constant, and it has this thing, okay, which we call the stress energy tensor. And we didn't quite discuss what the stress energy tensor is, but we argued that you can think of somehow the 0,0 component of this as being related to the density. Okay, we'll try to make that connection a little more precise today. Okay, so in a sense, you are really talking about the left-hand side is Einstein's tensor, which involves second derivatives of the metric if I calculate it in some coordinate system. And so in a sense, it really is like this Laplacian acting on phi. It's some second derivatives acting on the metric, which I'm solving for in terms of, given some particular source or given some particular stress energy tensor, I'm trying to find out what that metric is. And lastly, we said, okay, if you have the laws of electromagnetism, you can upgrade Maxwell's equations to be compatible with Maxwell's equations in an arbitrary gravitational field. Okay, and this arbitrary gravitational field, the way you implement it is you use something like this. Okay, so instead of just partial mu f mu nu is j nu. Okay, this cannot be right in on an arbitrary manifold, right? You need to upgrade it because this is coordinate dependent. Okay, So if I want to upgrade it in such a way that the left-hand side is a coordinate independent vector, the way to do that is to upgrade this partial derivative to an affine connection. Okay, this partial mu acting on F union. Okay, why does this not make sense? Well, we saw why this doesn't make sense, right? The reason why we define this derivative is because we had no way to connect vectors or tensors at different points in the manifold, unless you define a notion of parallel transport. Okay, and in some coordinate system, if you choose the gammas to be 0, then indeed this is what you would get. But in a different coordinate system, it would not be true. Okay, that the left-hand side of this equation was of this form. Okay, so so this is the most general way to write this, and this is valid in any coordinate system that you choose. Okay, any arbitrary coordinate system that you choose, this is the right extension of Maxwell's equations. Okay, it can be that in some coordinate systems it looks like this. Okay, but in general, and this will happen at some point on the manifold. It may not happen at all points simultaneously that you can write it this way. Okay. Okay, and then there's something, the other two Maxwell's equations can be written using something called a Bianchi identity, which we won't discuss, but it's kind of the analog of the Bianchi identity that we saw for the Riemann curvature tensor. Okay. All right, so today what we're going to do is we're going to do exactly this. We're going to start exploring the detailed meaning and implication of these laws. Okay, and what we're going to start with for today is to examine the laws. We'll make a simplifying assumption first, okay, rather than complicate things. We'll assume that there are no non-gravitational forces to worry about. So for example, we'll turn off electromagnetic fields. So we'll just assume that we're talking about, let's say, either particles which are not charged or particles, there are no electromagnetic fields present, right? And we're just looking at the motion of particles in gravitational fields. And we saw earlier that a genuine gravitational field is one which produces curvature. That's how we should think of genuine gravitational fields. Okay, anything which is not producing curvature is a fake gravitational field. If you change your coordinate system, you can get rid of it. Okay. Okay. So let's look at those laws that we just wrote down. Okay, and we'll study them first in the absence of non-gravitational forces. So the first equation, okay, is of this form: m del u is 0. Okay, so now I've set those non-gravitational forces to 0. Okay, so this should be the analogous to. Now remember that this still captures the effect of gravitational fields. It doesn't capture non-gravitational forces, but it still captures the effect of gravitational fields. Okay, where are those gravitational fields being captured? So genuine gravitational fields will give you a metric. Okay, where the metric cannot be simultaneously set equal to, let's say, eta mu nu everywhere. Okay, it can't be set to the so-called flat metric. Okay, so we'll see that this metric is actually what we call a flat metric. Okay, so eta being everywhere this. Okay, this is what we call a Minkowski metric. Okay, and we'll see why this metric is flat or it has no curvature. Okay, roughly speaking, since the curvature involves derivatives of the metric, if you have a constant metric everywhere, it has no curvature. Okay, so so now the argument is that supposing g mu nu is not flat. Okay, that is g mu nu in general, if I write it in some coordinate system, it depends on x. Okay, of course we've seen that, you know, by changing coordinates, you can start with something like this and go to something which has which depends on x. For example, in Ringler coordinates, right? We've seen that the same metric in Ringler coordinates is of the form it has some coordinate dependent coefficients. Okay, but still now in the Riemann curvature tensor, it doesn't matter whether you compute using this coordinate basis or this coordinate basis, you will still get the same answer. Okay, you'll still get the same answer, and that answer should be 0. Okay, the Riemann curvature tensor should be 0, no matter which coordinate system you use to compute it. Okay, this is the advantage of using objects which are coordinate system independent. Okay, you might have to express them in a particular coordinate system, but if the Riemann curvature tensor is 0, that means the tensor itself is 0. Okay, if that's true in one coordinate system, it must be true in any other coordinate system. Okay. Okay, so now suppose we have a gravitational field or some metric which has a non-zero curvature. Okay, that non-zero curvature necessarily means that you have these connection coefficients, and these connection coefficients cannot simultaneously be set to 0 everywhere in space. Okay, so this derivative, okay, will look like m del u. Okay, instead of just being something like m d square x dt square, this will already contain derivatives of the metric. Okay, and we'll see that those derivatives of the metric give you something analogous to a gravitational potential, okay, or a gravitational force. Okay, so we'll work this out later, but we'll show that basically this equation, it should capture everything about motion of particles in gravitational fields. Okay, so secretly this equation will contain things like this in some limit, okay, which is gravitational potentials and effective gravitational potentials on the motion of particles. Okay, so the geodesic equation actually captures those effects. Second is we have Einstein's equation, okay, which is this Einstein tensor is equal to some 8 pi g over c to the 4 t to 0. Okay, I'm writing the c here, but I'm going to drop it. From now on, I'll just use work in units where c is equal to 1. Okay, so we have something like this, and this is analogous to calculating the Laplacian of the potential and equating that to 4 pi g and rho. So you use this to solve for, given a matter distribution, what is the potential, or given a stress energy tensor, what is the metric. Okay, we're trying to solve for the metric. Okay, so so now let's try to understand. Okay, so again, we have no other forces, right? We only have gravity. Okay, genuine gravity means there's curvature. Okay, in general, if you have curvature, the components or this tensor will be non-zero. Okay, and so some types of matter will source curvature. That curvature will cause particles, okay, to feel the effect of a gravitational field. Okay, so we'll work out all these consequences in detail, and we'll try to get a detailed understanding for this sort of hand-waving intuition. Okay, so in the absence of any external forces, particles follow geodesics in curved space-time. Right? This is obvious. So you have to solve both these equations simultaneously. Okay, and if we just look at this equation, what it's telling me is, given a metric g, okay, this equation is now just saying del u is 0 for a particle. This is just the equation, geodesic equation. So it's telling you that particles move along geodesics. Okay, so that's what that law is telling you. In the absence of external forces, non-gravitational forces, particles will just follow geodesics. Okay, so this is just a consequence of that law that we wrote down. Okay, that particles will follow geodesics. But these geodesics are now in general in a curved space-time. Okay, they're not necessarily in a flat space-time. The metric is not necessarily just eta mu nu. Okay, or eta mu nu up to a coordinate transformation. It's something else, okay, other than just eta mu nu. The second thing is, from Einstein's equation, okay, we find that we actually have to solve for what the metric is. We don't a priori know what the metric is. Okay, in special relativity, you assume that the metric everywhere is eta mu nu. Okay, in general relativity, you're trying to solve for what that metric is, and the distribution of particles or sources actually produces a gravitational field which produces curvature, and I have to solve for, given that curvature, what is the metric. Okay, so the curvature of space-time depends on the matter or energy content. Okay, that's what this equation is saying. It's equating something which depends on curvature to something which is like the matter or energy content, matter density or energy density. Okay, and so literally matter and energy is producing curvature in space-time. Okay. And what you need to do with these equations now is you need to simultaneously solve them. Okay, so if you have many particles, okay, many particles, each of those particles is following an equation like this. Okay, it's following a geodesic equation, but each of these particles is also contributing to the matter or energy density. Okay, so as it moves, it changes the matter or energy density, and you need to solve this equation for the metric. Okay, so this equation has to be solved for the metric. This equation has to be solved for the velocities of the particles or the trajectories of the particles, and you have to solve both simultaneously. You can't just solve one by itself and the other by itself, right? Because as the metric changes, the particle's motion changes. Okay, as the particle's motion changes, the metric changes. So you have to solve both equations simultaneously. Okay, you can't just solve one by itself. Okay, so you need to simultaneously solve for the metric and the motion of all particles to find their coordinates. Okay, so this is what's unique about general relativity, is that the metric on the manifold is not given to you a priori. Okay, in special relativity, the metric is given to you. Okay, or in Newtonian mechanics, the spatial metric is given to you. Okay, it's just something like this in Cartesian coordinates. Okay, so the metric is given to you. What's unique about general relativity is now we have this principle that there is no prior geometry. Okay, the geometry or the metric of space-time depends on what the particles in that space-time are doing. Okay, and what the particles in the space-time are doing depends on what the metric is. Okay, so both these things have to be solved for simultaneously. Okay. Any questions here? Okay, so so note something. Okay, these equations are coordinate independent. Okay, just by the way we wrote them, we can clearly see that these are coordinate independent quantities, right? The left hand side of this is a vector. Vectors exist independent of any coordinates that you assign to them, and we're saying that that vector is a zero vector in the absence of external forces. Similarly, the left hand side of this equation is a tensor, and the right hand side is also a 2-0 tensor. And so again, these tensors are equal to each other. It doesn't matter what coordinate system you use to describe them. These tensors are always the same. Okay. So although although the equations are coordinate system independent, okay, to solve them and to kind of visualize or understand what the metric is, it's necessary that you want to express them in some particular coordinate system, right? For example, whenever we talk about vectors in usual Euclidean space, right, I can always say, okay, this is a vector, but that's not very helpful for you if you want to write down an equation, right? You need to write down some components of this vector. So I need to choose a coordinate system. Once I choose my coordinate system, I can write down what the components of this vector are, and then I can kind of work out some numerical equations that relate the components of this vector to other things. Okay. So similarly, what we will want to do is we'll want to choose some coordinate basis. Now, the point is, it doesn't matter what coordinate basis you choose. Okay. This is what's unique to general relativity. In special relativity, you had to pick out particular classes of observers. Okay, these were the inertial observers. And for those inertial observers who have these particular coordinate systems, those observers, the laws took a particular form for those observers. Okay. In general relativity, you can choose any coordinate system you want. It doesn't matter which one you choose. Okay, you choose any one you like. Of course, the problem might be more difficult in one coordinate system, might be simpler in another coordinate system. But now what you can do is you can always translate between one coordinate basis and another coordinate basis using the tensor dictionary. Okay, so now we have this general dictionary for components of a tensor, right? So if I want to compute, if I go from coordinate system x to coordinates y, right, we've seen that the components of the tensor, okay, very schematically, right, now in general relativity will obey something like this, right? There'll be partial y mu n, partial x nu 1, something like this. This is for upper indices, okay, times the tensor in the old coordinate system. This is expressed in the x basis, this is expressed in the y basis. Okay, once you have this kind of dictionary, you can always translate from one coordinate system to another. Okay, the components can be translated from one coordinate system to another. Now, the other thing is, it's possible that because of the topology of the manifold, yeah, go ahead. A little larger? Okay, sorry. Okay, I'll just zoom in so that you can see it. Okay. Yeah. Okay. Now, the other thing is, because of the topology of the manifold, it may not even be possible to cover the entire manifold with one coordinate system, as we've seen before. Okay, so sometimes you might have to solve in one coordinate patch, and then you have to write down transition functions in a separate coordinate patch, and you solve in two different coordinate patches, and you patch together the solutions. You match them in the overlap regions. Okay, so you might have to do something like this. You might have to patch together solutions in different coordinate charts. Okay, if you can't cover the entire manifold by one coordinate chart. Okay, now obviously one thing is really clear, right? If you want to solve these equations simultaneously, it's going to be very difficult, right? Because you have to simultaneously solve for the motion of particles. These are coupled differential equations now in a particular coordinate system. So you have to solve these coupled differential equations. Okay, and that's going to be very difficult. So in general, what you want to do is you want to simplify this. Okay, you want to simplify this. So the way we simplify is we say that let us assume that the form of the source is given to us. Okay, let's assume that the form of the source is somehow given to us. Okay, this T20, even though T20 responds, or the stress energy tensor responds to the metric, because the motion of particles depends on what the metric is. Let's assume that somehow someone has told us what that stress energy tensor is. Okay, after you've taken into account the fact that it responds to the metric. And we plug that in here, and then we just directly solve this equation for the curvature. Okay, so this is kind of analogous to, okay, so we'll basically solve Einstein's equations to find simple forms of the metric G with some fixed source, okay, some fixed T mu nu, which we are given what this is at all points on the manifold, which means we're given for all values of x and t, okay, in a coordinate system, what is this stress energy tensor? Okay, we're given what that is. And then we solve for the metric. Okay, so given this, we solve for the metric. Okay, so this is analogous to if you're given a fixed source, okay, like the sun, okay, the source is fixed, and you have a test object like the Earth going around, okay, you first solve Poisson's equation given, let's say, the density distribution of where the sun is present. Okay, let's say you want to treat it as a point mass, then you just assume that this density is proportional to delta cube of x minus x prime, where x prime is the location of the sun, and you multiply this by the mass of the sun. Okay, so this gives you a point mass density. So you can solve Poisson's equation. Okay, in Newtonian mechanics, you'd solve Poisson's equation, and you'd find out what the potential is. And what would you find for the potential if you had a point source? One by r, right? So it's just going to be actually 4 pi gn by 4 pi. So if I'm trying to find the potential at some location x, okay, it's going to be 1 over 4 pi x minus x prime. Okay, mod of this. Okay, this is basically the Green's function method. Have you seen the Green's function method? Maybe in your electrodynamics class, right? It's basically a way of solving the Poisson equation for point sources. Okay, so and the other thing is, once you have the solution for a point charge, okay, you can superpose many point sources, and you can find out what is the effect of, or what is the gravitational field due to many point sources, right? I can now take a distribution which involves many point sources. So many point sources at different locations, xi, okay, with different masses mi, and I can figure out what the gravitational field due to all of those will be. Okay, and that's also going to be easy to see. It's going to be some sum. Okay, the gravitational field will be some sum over those particles mi. Okay, sorry, here I should have had m sun. Okay, so I'll have mi. Of course, I'll have my g Newton over 1 over x minus xi. Okay, so this is basically a superposition of 1 over r potentials. Okay, a superposition of many 1 over r potentials. And you can have this superposition of many 1 over r potentials. And basically the point is, once you know how to solve it for a single point source, you can figure out how to solve it for many sources. Okay, but the key thing when you solve this equation is the reason why you can superpose solutions is because these equations in Newtonian mechanics are linear equations. Okay, which means that if I sum over many potentials and sum over many charges, okay, that will also satisfy the equations. Okay, so basically if I have a combination phi1 rho 1 and a combination phi2 rho 2, then phi1 plus phi2 is the solution to these equations when the mass distribution is rho 1 plus rho 2. Okay, that's because these equations are linear. Okay, if the equations were non-linear, this would not be true. Okay, so Newtonian mechanics has some simplicity. Okay, Newtonian gravitation has some simplicity. Okay, as we'll see, in general relativity, you don't have this simplicity. Okay, the equations will be non-linear in the metric. Okay. Okay, but the idea will be very similar, right? So we'll start with some source. Okay, we'll start with some source, and we want to solve for the metric. Okay, so given some source like the sun or some kind of stress energy tensor associated with the sun, we want to find what the metric is. That is, we want to find the gravitational field at the location of the Earth. Okay. So we want to find. This is what we want to do. We want to find the gravitational field sourced by some stress energy tensor. Okay. So once we have this metric, okay, once you have the metric, now you have a geometry associated with this space. Okay, you have a geometry associated with the space-time. You have a metric on the manifold. Okay. And now what you can do is now any test object like the Earth moving in this gravitational field, I can now find the motion of the test particle like solving for the Earth's motion in the gravitational field of the sun by solving the geodesic equation. Okay. So now for the test objects, okay, I can solve this equation. This affine connection is in the presence of that metric G, which I solved for. Okay. So I can now find so I can solve this equation to find, let's say, parametrically the trajectory of the Earth or any general particle in some gravitational field. Okay. So this would be analogous to solving, let's say, this equation. The mass times acceleration is mass times gravitational field. Okay. And as we've seen, gravitational mass and inertial mass are the same. So really what you're doing is solving a geodesic equation in curved space-time. Okay. That's going to be, well, we haven't proved that. We'll show that this is true. Okay. So this method of doing this, right? What is the trick that we did? Okay. The trick that we did is somehow we said that the stress energy tensor that we are given, okay, is somehow correct. Okay. That is when we solve both these equations simultaneously. Actually, there's not two equations. This equation is if I have n particles, I have to solve n equations. Okay. And these n particles, all of them together will determine the stress energy tensor. Okay. So so the trick that we played here is similar to the trick that you play in Newtonian mechanics. You neglect what is called back reaction. Okay. So you assume that the sun does not feel the gravity of the Earth. Okay. So you can ignore the gravity of the Earth. Okay. So you have a source which is very massive and which is determining the gravitational field for everything else. Okay. And you're now finding the motion of test particles in that sort of background field set up by your source. Okay. So the approximation that we've made is to ignore the gravitational influence of the Earth on the sun. Okay. Or your test particles on the sources themselves. Okay. And so this is called ignoring gravitational back reaction. Okay. And to the extent that this is a good approximation, our method works well. Okay. Why would we do this? Well, because it really simplifies our calculations. Okay, it really simplifies your calculations if you don't have to simultaneously solve for the motion of the Earth and the sun and try to figure out what is the gravitational field as both of them are moving. Okay, that becomes quite complicated. There is a method to solve this, the two-body problem in with a 1/r potential. This is exactly solvable in classical mechanics. It's not exactly solvable in general relativity. Yeah. You do use general relativity, but it's actually quite difficult. Okay, if you want to solve, let's say, so you might have heard that when LIGO detected black hole binary mergers, right? You have to solve for two objects which are kind of spiraling around each other, and as they're spiraling around each other, you're also emitting gravitational waves. Okay, so you have to solve for all of that, and so actually, what is done is you use approximations. Okay, you use some kind of approximations which maybe we'll talk about those approximations, but you can't solve these equations exactly for binary. I mean, you can solve them numerically. Okay, so people try to solve, this is called numerical relativity. You try to solve these equations, the same equations that we wrote down, you try to solve them numerically. Okay, but you have to assume still some initial assumption of what this T20 is, and then kind of evolve that in time. Okay, so what we're going to do is by breaking up the problem this way, by ignoring this gravitational back reaction, we've broken up the problem into, you first give me a stress energy tensor, and then I'll solve this equation for the metric. Okay, so that is a much simpler goal than trying to solve all these equations simultaneously. Okay, and so what we're going to do now is we're going to try to get a feel for, okay, we're going to try to get a feel for Einstein's equations. Okay, what does this equation tell us? Okay. And let me just pose a couple of questions, okay, that we'll try to answer, okay, about what I mean by saying let's try to get a feel for this equation. Okay, so what I'm going to do is I'm going to say write down some things that we want to try to understand, okay, and some of the things I'll explain as we go along, and some of the things will require longer explanations. Okay, so what I'm going to do is I'm not going to explain the longer things all today, right? Some of them might take a class just to explain. What I'm going to do is lay out a roadmap of what are the things we are trying to understand. Okay, what is it that we're trying to understand about this equation? Okay, that's what we're going to, and how does it differ from Newtonian mechanics? Okay, that's what we're going to try to understand. Okay, so if you look at the left-hand side of this equation, the left-hand side of this equation is the Einstein curvature tensor. Okay, so let's first look at that. So in this is some measure of curvature. Okay, and it's a measure of curvature at each point on the manifold. Remember that it's a tensor which is defined over the entire manifold, and at each point you can talk about the curvature properties at that particular point. Okay, so this is a measure of curvature and it's defined at each point on the manifold. Okay, and in any coordinate system, okay, we've seen that this g mu nu can be written. So whatever coordinate system I'm using, I put those indices mu nu here. And g mu nu, by definition, is the Ricci tensor R mu nu, right? Where the Ricci tensor itself was related to the Riemann tensor by contraction of indices, minus half g mu nu times the Ricci scalar. Okay. So let's recall what the Ricci tensor is. So this is Ricci tensor with upper indices. Okay. It's related to the Ricci tensor with lower indices by raising it with the inverse metric. Okay. So we use g mu rho to raise this index to R upper mu. And then we use g nu sigma to raise this index to R upper nu. Okay. So beware, R upper mu nu is not the same thing as R lower mu nu, right? As someone had asked in an earlier class, can we use different indices or different names for both of these things, right? We call this the Ricci tensor. Why are we calling this the Ricci tensor? It's really an abuse of notation, okay? But if you're clear about the location of the indices, you always have to remember that indices are always raised and lowered with the metric, okay? That's why we won't try to create new names for Ricci tensor with upper indices, okay? But always remember that something with upper and lower indices is very different in general relativity, okay? Okay, so now we have this in terms of the Ricci tensor. And now let's write the Ricci tensor itself in terms of the Riemann tensor. So it's g mu rho, g nu sigma. And this is the Riemann tensor. This is the Riemann curvature tensor. It's R with upper alpha, rho, alpha sigma. Okay. So by contracting these two indices of the Riemann tensor, we got the Ricci tensor, okay, which is R lower rho sigma. So R lower rho sigma was just equal to this. Okay, the contracted components of the Riemann tensor. Okay. Okay, and now this R with an upper index alpha we saw can be related to R with a lower index beta. Okay, R beta rho alpha sigma, where again I raise this beta using a G alpha beta. Okay, or I can think of this G alpha beta as taking a dot product between these two indices. Okay, these two dual vector indices. Okay, so this is how the Ricci tensor with upper indices mu nu is related to the Riemann curvature tensor. Okay, remember that the full information of the curvature is in the Riemann curvature tensor. Okay, the Ricci tensor has slightly less information than the Riemann curvature tensor. Okay. Okay, and now I had written down this complicated formula for what the Riemann curvature tensor is when you use the metric connection. Okay, so we had a general formula for the Riemann curvature tensor with an arbitrary connection, but when you use the metric connection, we saw that you can express the Riemann curvature tensor. Okay, this is the formula in Nakahara. I don't remember which in chapter 7. And the thing I told you was that there's a minus sign here. Okay, and there's also a typo in one particular index, okay, of this term. Okay, I think what I've written here is exactly correct. Okay, because I verified it again. Okay, so you can use this formula. Okay, so this is the Riemann curvature tensor. Okay, it's equal to some second derivatives of the metric partial square g beta alpha. It's pretty horrible looking. Okay, but it has the second derivatives of the metric, and then there is metric and then Christoffel connections. Okay, but these Christoffel connections involve first derivatives of the metric, and it's a product of two Christoffel connections. So it's order 1 derivative of the metric times order 1 derivative of the metric. Okay, so net every term in this has two derivatives. Okay, and it involves the metric. Okay, these terms are linear in the metric. These terms are non-linear in the metric. Okay. because each gamma will involve some g's. Okay, so partial g, partial g. Okay, so it's really a mess. You see that once you start getting into indices, right, it becomes a mess. Okay, the prettiness of the equations is when you write them in coordinate invariant form. Okay, in a particular coordinate system, the equations don't look. I mean, this is of course we're not specialized to any coordinate system. These rules are valid in any coordinate system, but already once you expand it out in terms of components, okay, it starts looking very messy. Okay. So the Ricci scalar is related to this this Riemann tensor with upper index, sorry, Ricci tensor with upper indices by G mu nu R mu nu. Okay, here I'm also, you know, taking the abuse of notation even further. I'm not even separating out a separate symbol for the Ricci tensor, for the Ricci curvature, and the Riemann tensor. Okay, all of these are different tensors. This is a type 1,3 tensor. This is a type 0,2 tensor, and this is a scalar. So this is type 0,0 tensor. Okay, but I'm using the same symbol R for all of them. The location of the indices and the number of indices tells me which type of which of these tensors I'm actually talking about. Okay, so if I have 4 indices, it's a Riemann tensor. It could be raised or lowered indices. I can always raise or lower with the metric. If it's 2 indices, it's the Ricci tensor. Again, it can always be raised or lowered with the metric. And if it's no index, then that's the Ricci scalar. Okay. Okay, so now let's look at the left-hand side of this equation. Okay, so the left-hand side of this equation is G mu nu, and the left-hand side in components is R mu nu minus half G mu nu R. Okay, R mu nu is this horrible mess. Okay, it's some inverse powers of metric times the second derivatives of the metric. Okay, and the Ricci scalar involves this Ricci tensor, okay, contracted with the G mu nu. Okay, so roughly all of these terms contain 2 derivatives. Each term contains 2 derivatives. Okay, every single term in this expansion will contain 2 derivatives. Okay, because the derivatives only come from either here or here. Okay, there's nowhere else where the derivatives come from. But it's highly nonlinear in the metric components G mu nu. Okay, so besides the fact that this is quadratic in the, you know, sort of metric components, even every time I raise the indices, I'm using the inverse metric. The inverse metric is highly nonlinear in the lowered metric components. Okay, because if I'm taking G alpha beta, and if I write this in terms of the lower components, G alpha beta is the inverse metric. So if I think about the matrix G with lower indices, okay, that is some matrix, and I take the inverse of this matrix. Okay, and the inverse of these matrix I say has components of that. It's some matrix, and I refer to the components of this matrix with alpha beta. And now, what are the components of this matrix in terms of the original matrix? Well, it involves some things like the cofactors of this matrix divided by the determinant of this matrix. Okay, so you can see that the cofactors of this matrix, so if I want the cofactor of this element, it would involve the determinant of this matrix divided by the total determinant of G. Okay, so this entry of the inverse matrix is this cofactor, which is this determinant, okay, with an appropriate sign, divided by the full determinant of G. Okay, that is obviously a highly nonlinear function which involves many products, right, of all these components of the metric. Okay, so so if I think about solving this, okay, this G mu nu in terms of the inverse metric components, it's a highly nonlinear combination of those sorry, not the inverse metric, in terms of the metric components, it's a highly nonlinear combination of those metric components. Okay, so it's some very highly nonlinear left-hand side. The problem with nonlinearity is that if I find one solution to these equations, to the Einstein's equations, I cannot superpose it with another solution. Okay, so I can't use one solution to generate other solutions. Okay, which you could do in Newtonian gravity. Okay, so the solutions cannot be superposed. Okay, that is, if I give you one source T1 mu nu, and you solve these equations and you find the metric. Okay, you somehow solve these equations. They're nonlinear differential equations. You solve them, you find out the metric. And then I give you another source T2 mu nu, and you solve that, and you figure out what the metric is. Okay, but now if I tell you that my source is T1 plus T2 mu nu, okay, I added those two sources together. I added the tensors for those two sources. The solution is not going to be G1 plus G2 mu nu. Okay, so I can't superpose solutions. Okay, I have to solve this again. I have to start from scratch and solve this again. Okay, there's no easy way to get the solution for this, even if I know the solutions for this stress energy tensor and this stress energy tensor independently. Okay, so this adds to the complication of solving Einstein's equations. Okay, any questions at this point, either online or in class?
So the other way to say the same implication that we just got is to say that any kind of Green's function method won't work here. Is that right?
Yeah. Okay. So what Anish said is the Green's function method. That is, if I solve with a delta function source that we did earlier, that once you know it for delta function source, in Newtonian gravity you can solve for basically you find the 1/r potential, and you find that it works. Now you can superpose many point charges to get a density distribution and find the gravitational potential of that density distribution. That Green's function method doesn't work here. Okay, it doesn't help you to find the metric associated with, let's say, some delta function type source. Okay, it's not going to help you to solve the more general case. Okay, so you have to solve for each stress energy tensor. You have to solve for separately. Okay. Why is there nonlinearity in the system? Yeah, actually, almost everything in nature is nonlinear. Okay, to an approximation, we find linearity. Okay, now Maxwell's equations, it's true we find them to be linear. Okay, but even in modern quantum theory, when you try to understand what are the corrections to Maxwell's equations, you find that they're nonlinear. Okay, but usually the nonlinearities can be ignored in the sense that if your electric fields and magnetic fields have a small amplitude, okay, then you can ignore these what are called quantum corrections to Maxwell's equations. Okay, so in general, you actually always do have nonlinearities. Okay, Einstein's equations by necessity, you cannot write down anything that is coordinate invariant, right, which doesn't have that nonlinearity built into it. Okay, so this is sort of giving you a physical principle which directly gives you the nonlinear form of the equations. Okay, and that is quite something that's rather unique to Einstein's equations. So, I mean, rather the question is the reverse. You should be surprised that Maxwell's equations are linear. Why are they linear? Right? The general thing is I can have nonlinear differential equations. Why do they have to be linear differential equations? Okay, and it's only true to an approximation that they're linear. As we'll see, even with Einstein's equations, you can take some approximations in which they are linear. Okay, you can take some approximations in which they're linear. These are called the weak field approximation, when the gravitational field is not strong. Just like I told you, when the electric field is not strong, you could take in that approximation, you get Maxwell's equations. However, if you work in that limit where the gravitational field is weak, okay, and you get linear equations, you are not able to see in that form the full symmetry of general relativity is hidden from you. The diffeomorphism invariance, the coordinate invariance, that gets completely hidden from you. Okay. In fact, if we had started down the route that we had first discussed, okay, of formulating a law of gravity which is a merger with special relativity, we would have got the linearized approximation to Einstein's equation. Okay, that's what we would have got, right? Remember, one of the principles that we took when writing down those laws in the very beginning of the course was that the laws are linear in the fields. Okay, we said that may or may not be true. Okay, and if you assume it's linear in the fields, you can write down and you can truncate after linear order. Okay, but you can add higher order terms like something which is higher order in the electric field or magnetic field or gravitational field. The beautiful thing about Einstein's equations is automatically, once you say that the laws of physics are coordinate system invariant, it directly gives you the full nonlinear equations in one go. Okay, you don't have to guess term by term in the nonlinearities what the coefficients are. Okay, the other thing about these equations is that they are second order differential equations. They're second order in the derivatives of G. So it's non-linear second order differential equations. Okay, so you might have studied in, let's say, your math courses, you would have studied second order differential equations. A very simple form of a second order differential equation is a harmonic oscillator. Okay, but this is what is called a linear harmonic oscillator. Okay, and the solutions to this are known. Okay, you just get things like a cosine omega t plus phi, let's say. Okay, this is a general solution with some, and since it's a second order differential equation, you have to specify two initial conditions. At t is equal to 0, you have to specify the amplitude and the phase, okay, of this harmonic oscillator. Now, if you had added, the other thing is, now if I get one solution, I know that if I have another solution, x prime is, let's say, a prime cosine omega t plus phi, right? So, or phi prime. So what you have seen some examples of is, for example, a cosine phi, and if I choose phi prime is b by is some pi by 2, right? I can have b sine phi, and my general solution can be a superposition of arbitrary, cosine omega t plus sine omega t. My general solution is some linear combination of cosine omega t and sine omega t. Okay, I can superpose solutions. Okay, this is my general solution. Okay, this would not be true if I had added what is called an anharmonicity. Okay, this would be a non-linear second order differential equation. Okay, and this basically, if you decompose this x in Fourier mode, you see that in the linear differential equation, this oscillates with only a single frequency. Okay, once I add this kind of anharmonic piece, what I'll find is the general solution, not the general solution, but a particular solution if I solve for in x, it would involve terms which have many Fourier modes. It would have not only the natural frequency of the oscillator omega, but it would have other frequencies like 2 omega, 3 omega, many other frequencies would show up. Okay, if I take x of t and take its various Fourier components. Okay, and typically we don't even know how to solve this equation in general. Okay, we can only solve in the limit where this is treated as a perturbation. So you assume there's some coefficient lambda and lambda is small. In these approximations, you can solve these nonlinear differential equations. Okay, a general nonlinear differential equation, especially when these coefficients are large, we don't really have a general technique to solve them. Okay, the techniques that we have work only for linear differential equations. Okay, so there's no general technique to solve nonlinear differential equations. You can solve in perturbation theory, okay, but that basically is, so in general, imagine that this was a complicated equation, okay. Imagine that it was x double dot is equal to minus e to the minus lambda x, okay. Or let me just write down a nonlinear differential equation. So let me write down x double dot is equal to minus 1 e to the minus lambda x. Okay, so let's imagine I'm trying to solve this differential equation. Okay, now what this is, what this equation is instead of my restoring force just being proportional to x. Okay, so this is like my restoring force, right? Previously we said my restoring force is proportional to x. So if I think about a spring, right, and this is a block, okay, if I displace it some positive amount, depending on how much I displace it, there's a linear restoring force. That's the assumption that I make. Okay, now with this assumption, what I'm saying is now the restoring force is such that if x becomes sufficiently large, okay, then my restoring force actually doesn't go on increasing, right? My restoring force doesn't go on increasing. This 1 minus e to the minus lambda x, as assume lambda is positive, as x becomes very large, this term is very small. So this approaches a constant. Okay, so if I plot my restoring force as a function of displacement, initially it increases. Okay, it increases linearly, but then it saturates to some constant. Okay, that is, the restoring force doesn't exceed a certain amount. Okay, and basically if I'm at very small displacements, this is linear. Okay, and then I am solving a linear differential equation. As I start moving to larger and larger x, my nonlinearities start becoming important. Okay, and eventually as I get to a distance scale x is 1 by lambda, okay, so somewhere here 1 by lambda, all the nonlinearities are important. That is, I can, you know, to an extent, if x is much less than 1 by lambda, then I can expand this. Okay, basically what I'm saying is lambda x is much less than 1. Okay, then I can expand this in a series. Okay, and if I expand it out in a series, then this looks like -1 plus minus lambda x plus minus lambda x whole square by 2 factorial plus so on. Okay, and so at leading order these cancel out, and what I get is minus lambda x minus lambda square x square by 2 and so on. Okay, so you see that in some approximation, in some approximate regime of displacements, okay, it's linear plus some small correction. But as I get to larger and larger displacements, all these corrections become important. Okay, so it's the solution itself, right? So basically when I solve, I don't know what the amplitude of my displacement is. So I'm only solving, my solutions are only valid for small displacements. Okay, and you're right that in perturbation theory, you can solve this if I take a slightly larger displacement, or I can find corrections to basically my my naive solution. Okay, but the full nonlinear differential equation, we don't have a technique to solve it. Okay, you can expect that there will be some oscillating behavior, but that oscillation will involve many Fourier modes. Okay, it won't involve a single frequency omega. Okay, I mean, this is a restoring force after all, which means that you expect that I'll displace it. Even if the displacement is very large, I'll come back, overshoot, go to the other side and move. But I won't necessarily have symmetric behavior, right? All kinds of things can happen. Okay, now to solve these equations, okay, these are second order differential equations. So even though they're nonlinear, you still have to specify some boundary conditions, okay, if you want to solve them, okay, or yeah. So if you have a coordinate patch, for example, you're only solving the coordinate patch. So if I'm solving, for example, on a circle, let's say I have one coordinate patch which is like this, right, and the other coordinate patch which is like this, right? As we saw in the beginning of the course, you exclude the point at theta is equal to 0, or you exclude the point at theta is equal to pi. And you have to patch these solutions together. Okay. So instead of boundary conditions, you're sort of patching solutions together, okay, in different regions on a manifold like this. Okay. Okay, the other thing is this equation is local. Okay, that is, this curvature tensor is a locally defined curvature, which means at every point on the manifold, you're given the curvature because you're given what T mu nu is at every point on the manifold. Okay, so I know what the curvature is because I know T mu nu, and now I have to solve this for what is the I have to solve this for what is the metric, okay, at all points in spacetime. So we have a local curvature because we're given a local stress energy tensor. Okay, this seems like an obvious statement, but it's not. For example, if I take my harmonic oscillator, okay, which looks like this, the important point is that the force that I feel, okay, cares about the displacement of the oscillator at time t. Okay, that is, if I'm calculating the force at time t, I care about what is the displacement of the oscillator at time t. Okay, there's no lag between the force and the displacement. Okay, but I could have had a lag between the force and the displacement. Okay, so I could have had something like x, but not at time t, but at t minus some tau. Okay, and I'm solving for x double dot of t, not of tau. Okay, so this would have been a lag. Okay, so that is basically the force responds to where the oscillator was at an earlier time. Okay, so this equation would be called non-local. Okay, so the equations that we are solving are still local. Okay, that is, if I have a stress energy tensor at one point in spacetime, that determines the curvature at that point in spacetime, not somewhere else. Okay. Okay, another point is that the Einstein equation only constrained this G20. Okay, that is, they only constrain this combination of the curvature. This combination of the curvature was the Ricci tensor minus half G mu nu R. But the full properties of the curvature are captured in the Riemann curvature tensor. Okay, not in this tensor. This only has a reduced dependence on the curvature. So the full Riemann curvature tensor has all the dependence. Okay, this has only part of the curvature encoded in it. Okay, so we are only telling you what, when you tell me what the stress energy tensor is, you're only telling me a part of the curvature, the full curvature, which is the Einstein tensor. This is not the full Riemann curvature tensor. Okay. Now, what happens to how do you fix the other components of the curvature? Well, it turns out that they get fixed by the boundary conditions that you assume on the metric. Okay, I have to check this, but I think this is true. In fact, so in general, so when we're solving the equations, these boundary conditions are sort of telling you if there are sort of fluctuations in the metric which are sort of escaping off to infinity. Okay, and these are exactly gravitational waves. Okay. Okay, now the other thing about why this is so mathematically hard is, see, the curvature in greater than 2 dimensions, okay, is very hard to visualize, right? We saw in 2 dimensions, we thought of the curvature by thinking about how you're embedded in 3 dimensions, right? So we thought of the curvature of a sphere, and we thought about how to imagine that as being embedded in 3 dimensions. If you can't embed in 3 dimensions, how do you visualize curvature? Okay, so obviously something with dimensions greater than 2 cannot be embedded in 3 dimensions in general, right? Curved 3D space, how do you embed it in flat 3D space? You can't. Okay. In fact, there are even 2-dimensional spaces which cannot be embedded in 3 dimensions. Okay. I'll give you an example of one in a tutorial sheet. Okay. So we saw, for example, a sphere has constant positive curvature everywhere. Okay. A saddle point that I discussed earlier, okay, is something that had positive curvature and negative curvature, and the product of the two was a negative curvature. And this was, I told you, a negative curvature at a point. Okay, but now can you imagine a space which has constant negative curvature? Negative curvature is not hard to imagine. This is negative curvature, right? The saddle is negative curvature, but constant negative curvature is much harder to imagine. Every point on the surface has to have the same negative curvature. That's harder to create, okay? Because this point will not have the same curvature as this point, okay? The radius of this circle and the radius of this curvature, they have to be the same always, and this has to be true at every point on the saddle, okay? That's not going to be true, okay? That particular space with constant negative curvature exists, okay? That space is called H2, okay? Just like the sphere is called S2. It's called hyperbolic space. And it turns out that you cannot embed this space in 3 dimensions. So you can't actually visualize what this space is, okay? You can't actually visualize the space easily. You can just visualize it locally, but you can't visualize it everywhere, okay? Locally, it has negative curvature. That's easy to visualize. Visualizing constant negative curvature, that's much harder, okay? So there are some spaces which are hard to visualize. I mean, surprisingly, even 2-dimensional surfaces exist which are hard to visualize, okay? And curvature in greater than 2 dimensions is even more impossible to visualize. Okay, so you can't really visualize what 3-dimensional curvature is, 4-dimensional curvature is. First of all, you need more. We've seen that the Riemann curvature tensor, which contains all the information of curvature, has n square into n square minus 1 by 12 entries. Okay, so you need more than one number to describe curvature at a point in greater than 2 dimensions. Okay. So it's hard to even understand what those numbers mean. Okay, so you have to trust the mathematics a little bit. We understand intuitively what the Riemann curvature tensor is, but now can I relate every single time I draw something? Can I visualize that curvature? That becomes much harder. Okay, so it's very hard to visualize even with the Riemannian metric. Okay, so even with metric signature being all +1s. Curvature in D greater than 2 dimensions, even in 2 dimensions, can be very hard to visualize. Okay, and now we're talking about pseudo-Riemannian manifolds. Okay, that is a manifold with this kind of metric signature, and this is even more hard to visualize. Even if we talk about what is called flat pseudo-Riemannian manifolds, okay, that is basically your Minkowski metric. G mu nu is eta mu nu. Even this was quite hard to visualize. Okay, we had some tricks on how to visualize this. right? Because basically what you're thinking about is if you think about x and t as your coordinates, right? You have to remember that all these points on the light cone, they are at the same at zero distance from each other, right? Because ds square is equal to d tau square minus dx square on the light, sorry, is dt square minus dx square. This is 0 on the light cone. So these points are at zero distance from each other. Okay, how do you visualize that? You can't really visualize it, right? We're drawing some image to help us gain some intuition about it, but that doesn't mean we've really visualized it, right? So we have to make these kind of guesses of intuition wherever we can to simplify things and to try to visualize what it means to be in a space with this kind of metric. Okay, so when you talk about being in a space with this kind of pseudo-Riemannian metric, the prototype for that is to talk about Minkowski space. Okay, through our understanding of special relativity, we built some understanding of what Minkowski space is. But imagine now that we're trying to visualize a curved pseudo-Riemannian manifold. We're trying to visualize curvature of Minkowski space, okay, or curving Minkowski space. Okay, how do you visualize that? Okay, so we have to develop tools to help us visualize that. Okay, it's not easy. In general, it's not easy. In general, you cannot visualize it. You have to just trust the mathematics, okay, of and calculate using the techniques that we've developed. Okay, so I mean that might be a little disappointing, right? That after developing all this notion of curvature, we can't really visualize this curvature. Okay, we understand what it means, but how do you think about it, right? At some point, you really can't, right? You just have to trust the mathematics. Okay. In some cases, when there is a lot of symmetry, when the manifold has a lot of symmetry, for example, like a sphere, right? You can partially visualize the spaces. Okay, so even this hyperbolic manifold, you can kind of guess what is happening at each point, but I mean, you can't really visualize the whole manifold, but you can still guess that each point has the same negative curvature. Okay, so when you have this kind of symmetry, the symmetry in this case being that the curvature is the same everywhere. Okay, so every point in the sphere is identical to every other point. Okay, so this is a symmetry. I can rotate the sphere and I would get the same symmetries. Okay, so these kind of symmetries, you can partially visualize these spaces, and this is great for building intuition. Okay, so when you have a lot of symmetry in a space, then sometimes it's easy to build some kind of intuition, okay, for what the curvature on this pseudo-Riemannian manifold means. Okay, so for example, we will look at two-dimensional slices, right? Like we're doing here with x and t. We're ignoring the y and z, and we're trying to build intuition just in x and t, right? And we kind of get what will happen in y and z. So in general, the takeaway is that you do have to rely on mathematics a lot more in general relativity. Okay, we've developed the formalism, we understand what things mean, but visualizing it becomes harder. Okay, so now this is a list of things that we need to do, which will take a lecture by themselves just to do. Okay, so we need to intuitively understand the stress energy tensor. Okay, we don't quite know what the stress energy tensor is yet. I just told you that T00, something like T00 is rho, but obviously this cannot be a coordinate independent statement. In some particular coordinate system, it can be rho. But if I switch coordinate systems, the components of T mu nu get mixed with each other, right? So this doesn't make sense at all to say T00 is rho. That can at best be true in one coordinate system, not in every coordinate system. Okay, so we'd like a better understanding of what exactly we mean by the stress energy tensor. The other thing is we'd like an argument for why it is that Einstein's equation involved an equality between the curvature tensor and the stress energy tensor, right? What do we mean by why this particular equation? Well, two things could have been different. One is all I need on the left-hand side is some measure of curvature, and that measure of curvature didn't have to be the Einstein tensor. Why couldn't I use the Ricci tensor, for example, right? Why that particular combination? Why that particular combination of r mu nu minus half g mu nu r? Why is that the thing that appeared over here? All I need is some 2-0 tensor that is some measure of curvature. Why this particular combination? Okay, that's one thing we'd like to understand. Another thing that we'd like to understand is this is the same Newton's constant that appears over here. Okay, why is it 8 pi times that Newton's constant? Why isn't it some other value times that constant, right? So we'd like to understand two things, okay, in particular that we'd like to understand. For example, why not some other curvature tensor over here? And why not some other constant, over here. Okay, I mean, you can say I'm equating a 2-0 tensor with another 2-0 tensor, but that still doesn't tell me why it's Einstein tensor and why it's this particular constant over here. Okay, this constant we will argue, okay, and we'll argue this also, is that we would like to argue that Poisson's equation, that is Newtonian gravity, emerges in some limit of Einstein's equations. Okay, in some limit of Einstein's equations, it's possible to find Poisson's equations. Just like in special relativity, if I take the limit v much less than c, I get Galilean relativity. I get Newton's laws in the original form. Okay, so in some limit, we'd like to argue that Poisson's equations emerge from Einstein's equations, and we'll see that the appropriate limit in which this happens is when the gravitational field is weak. Okay, we have to define what we mean by weak, and the test particles that we're talking about are slowly moving. Okay, they're moving with speeds much less than the speed of light. In the combination of these two limits, okay, you will get exactly Newton's laws of gravity. Okay, that's something else that we'll see. Okay, and in fact, when we show that we get Newton's laws of gravity, that will actually determine what this constant is over here, right? Because ultimately, we are getting Newton's gravitational constant here. So somehow we have to connect it with the limit where we get Newton's gravitational laws. Okay. So arguing that we get Poisson's equations will actually determine what this constant is over here. Okay. But not only will we show that you get Newton's laws, we'll show that you just like we expanded this corrections, right? And you had x plus x squared plus x cubed. What we'll see is that instead of taking the exact form of the nonlinearity, you can get these perturbative corrections to Newton's gravitational laws. Okay, so you can show that not only is the gravitational force 1 by r, but there's also a gravitational potential which goes as 1 by r cubed. Why haven't we detected this 1 by r cubed? Well, it's an extremely weak gravitational potential. What we'll see is that this correction for typical bodies for which we can measure the gravity, like the Earth, Sun, this correction is very small, practically so small that you can't neglect it. You can neglect it within the experimental error that we've been able to achieve on measuring the gravitational field of the Sun. Okay, if we had high enough precision on measuring gravitational fields, we could have already detected these corrections. Okay, as I'll discuss, there is one effect when we observe the motion of Mercury around the Sun. Mercury is very close to the Sun. So this correction, the drop off in 1 by r versus 1 by r cubed, is not as much for Mercury as it is for the Earth. Okay, so for Mercury, this correction actually can be slightly important. Even for Mercury, it's still a tiny effect, but it's measurable. Okay, and the measurable effect is instead of the orbit of Mercury being a perfect ellipse, the ellipse actually precesses with time. Okay, in fact, it precesses because of the gravity of the other planets, but this precession also has an extra correction from this correction to general relativity. Okay, and in fact, this precession was known, but the explanation for it was not known, and general relativity exactly predicted what that correction should be. Okay, to the precession. Okay. So you're not only predicting Newton's laws, okay, but you're predicting corrections to Newton's laws. Just like special relativity not only predicts Galilean relativity in some limit, but it also predicts corrections to Galilean relativity. Those corrections are suppressed by powers of v by c. Why did we never know about special relativity before? Because the speeds of everyday objects are much less than the speed of light. Okay. Okay. What we would like to do, okay, another thing that we'd like to do is we'd like to solve Einstein's equations for some simple cases. Okay, so we'll make some assumptions on the source properties. What is the stress energy tensor? We'd like to make some assumptions and solve. Okay, so maybe we can't superpose solutions, so it's not going to help us with, if we find a delta function solution to solve it. But at least we'll gain some intuition about what happens in certain specific cases. So we'd like to solve, for example, let's say when there's no source, okay, when T mu nu is 0. Okay, now one easy thing to see is that the flat metric is actually a solution to Einstein's equations when there's no source, right? Because the left hand side G mu nu, okay, now we're equating it to 0. Okay, and so we've already, I'm giving you a solution to Einstein's equations already, okay, when the sources are taken away. G mu nu is 0. Okay, if this involves second derivatives of g. Okay, so obviously one solution is g is a constant. Okay, or if I equate g mu nu to eta mu nu in some coordinate system, okay, then this this is a solution to the vacuum Einstein's equations. Okay, so Minkowski spacetime is a solution to Einstein's equations in the absence of any sources. Okay, so so what we'll see is that the effect of gravity of the sun is a small correction to a Minkowski spacetime. Okay, it's a small correction to a Minkowski spacetime. So what we'll study that as flat metric plus some kind of what we call scalar perturbations. Okay, so some perturbation to Minkowski spacetime, which will basically cause a warping or a curvature of Minkowski spacetime, but that curvature is small enough. In the limit that the curvature is sufficiently small, it'll really, the equations we get will exactly look like Newton's laws, okay, of gravity. And we'll also see that the perturbations can be more complicated. They don't have to be scalar perturbations. They can be tensor perturbations of this form, eta mu nu plus some general perturbation h mu nu. And the terms that I'm ignoring are like h square times h mu nu and so on. So these are cubic in the perturbation. Okay. So basically, if I ignore these kind of cubic terms, okay, cubic and higher order terms, then I will get predictions that I can have solutions to Einstein's equations where this h mu nu actually looks like a traveling wave. Okay, it looks like a traveling wave. So I can get predictions of the existence of gravitational waves. What is this gravitational wave? It's a fluctuation in the metric. It's a traveling fluctuation of the metric. Okay, so I'll get solutions where h mu nu basically has wave-like behavior. H mu nu is something like sine omega t minus k dot x. Okay, so some kind of traveling wave solution. We'll see that you get these kind of traveling wave solutions. Okay, yeah. So the theorem of second order differential equations with boundary conditions guarantees that the solution is unique once I specify the boundary conditions, even for nonlinear differential equations. Okay, so the solution is unique for second order differential equations. So I guess you're talking about other vacuum solutions. Those other vacuum solutions, actually, you can think of them as, we'll discuss them. Okay, there are other things that people call vacuum solutions. But you can think of those vacuum solutions as really where I introduce some particular form of the stress energy tensor. Yes, it does. In fact, I'll talk about it. Let me come to that discussion. Okay, but with T mu nu is 0, the equations that I wrote down have a unique solution. Okay, and that's eta mu nu is 0. Okay, I should mention one thing. I assume something about the topology of the manifold. Okay, I assume that the manifold is R4. Okay, if the manifold is not R4, then you have to solve carefully. Okay, for what is the metric, you have to do it patchwise. And even if you solve in one patch and you solve in another patch, it's not guaranteed that you can patch together the solutions. So there might be what are called topological obstructions, because this equation is a local equation. It doesn't know anything about the topology of the manifold. So you solve in one patch and you solve another patch. If I can, somehow there's some impediment to patching these solutions together. Okay, that is, it doesn't work when I patch it over the entire manifold. Then you'd say there's a topological impediment to this metric being a solution to on this manifold. It might work on some other manifold, maybe it doesn't work on this manifold. Okay. Typically, that's not an issue we'll worry about because we're only solving Einstein's equations in one coordinate patch. We don't know what the full manifold of spacetime is. So we only solve in one region of spacetime. But it's important to note that there can be these obstructions, okay, topological obstructions to a metric. Okay. The other thing is when you if you ignore these higher order corrections, in the limit where I solve this, taking into account the scalar perturbations and tensor perturbations, that is exactly sort of the approach that we would have taken to formulating general relativity was exactly this. We were trying to guess some kind of h mu nu and we would have got an equation for h mu nu and those equations would have been linear. Okay, that is sort of like an approximation to general relativity. That approximation is something we would have got if we had started the traditional route. Assume special relativity, within the framework of special relativity, assume some tensor field and calculate the laws. Okay. the general relativity is much more deep because it has this new principle. The new principle being coordinate system independence, okay, of the laws of physics. Okay, this already, when you're saying the metric is eta mu nu, you're assuming in some particular coordinate system it's eta mu nu. Okay, so you've already lost that coordinate system invariance. You're working with a particular solution in the presence of a background stress energy tensor which you're roughly assuming is zero. Okay, so now I'll come to these other vacuum solutions. Okay, so the other vacuum solutions are, there's this particular type of stress energy tensor where it's some constant called a cosmological constant times g mu nu. Okay, this, you can imagine this form. Okay, now you can either think of this as being a source, or you could have thought of this as, instead of g mu nu on the left hand side of the equations, why not have something like g mu nu minus lambda g mu nu is equal to T mu nu, right? So I can either move this to the right side and think of this as a source, or I can just keep it on this side and say, well, I don't know why, I mean, like I argued earlier, right? I don't know why the right hand side had to be G mu nu. It could have been R mu nu, right? Or it could have been something else, right? I mean, in particular, I could have had this kind of combination. Nothing stops me from having this combination. And indeed, Einstein spent a lot of time trying to play around with this kind of solution. So this is called a cosmological constant. Okay, and at the time when he did this, he later spent a lot of time on this, and he basically gave up on this idea. Okay, he was trying to explain why the universe would be static, and later it was found that the universe was expanding. Okay, and it turned out that putting in this kind of term in the equation, he was trying to use that to get a static universe. Okay, it turns out that today we actually believe from experimental measurements that there really is such a term present, okay, in a cosmological constant present in Einstein's equations. And usually we don't think of it as being on the left hand side of the equation. We think of it as another source of energy density. Okay, and it's sort of a constant source of energy density. This lambda is a constant, and T mu nu is proportional to the metric. So this is also called a vacuum energy. Okay, vacuum energy or a constant energy density. We'll see why this terminology is appropriate. But this vacuum energy, really you think of as the energy density of empty space. Okay, it's the energy associated with empty space has some energy. Now, normally you don't think about the energy of empty space as being anything physically relevant, right? Because, for example, if I ask you what is the potential energy of a ball that I hold above the ground, I can always add some constant to it and say that there's this, fixed reference value of energy, and I have this extra energy from the potential energy of lifting it above the ground. That fixed energy is sort of not important, right? You don't think of it as important. But in Einstein's equation, that fixed energy is important. Okay, this is the only place in physics where that fixed energy is important. Why is it important? Because any form of energy or energy density, sorry, give me a second. Any form of energy or energy density causes a curvature of space-time. Okay, any form of energy density, even vacuum energy causes a curvature of space-time. Okay, so this is the only place in physics where vacuum energy is actually important. Okay, and we've actually measured a vacuum energy which is believed to be driving an accelerated expansion of the universe today. Galaxies are not only moving away from each other, they're accelerating away from each other. Okay, yeah. Yeah, I'll talk about it. But roughly speaking, the energy, so the universe is expanding, but even as it expands, the energy density stays constant. It doesn't dilute with the expansion of the universe. No, I mean, literally you think about like, okay, I mean, of course you can describe this in a coordinate independent way. Okay, oops. How do I turn off this low power mode? Okay. Yeah, literally you can think about an energy density at some point in space. Okay, this is stored energy. Okay, this energy you have no way to tap into it. Okay, but it can still cause a curvature of space-time. Okay, there is nothing else. You can't convert this to kinetic energy. You can't convert it to potential energy. You can't do any work with this. But it can still cause the metric to change, and that change of metric causes an expansion of space-time. Now, this expansion of space-time, okay, due to this this metric, I mean, is strange, right? Because normally, if you take matter particles, a matter density, As the universe expands, the particles move further away from each other, the energy density dilutes. Vacuum energy does not dilute when the universe expands. That's why it's a constant energy. Yeah, we'll discuss that. We'll discuss why it fits in with conservation of energy. In fact, in general relativity, the general principle of conservation of energy, okay, doesn't work when you just talk about conservation of regular matter energy. You also have to take into account gravitational self energy, and those two together are conserved. But usually when we're thinking about energy, we're not thinking about the energy, some energy associated with the metric, okay. The energy not associated with the metric, that is not conserved. Okay. In some appropriately defined sense, you can't think of gravity anymore in the way that you used to, right? So you can't. I mean, one simple example is Newtonian gravity. Things always attract. Why would things repel each other? If you want to cause an expansion of the universe, it's some kind of repulsive force, right? That is a solution only to Einstein's equations. You can't get that from Newtonian gravity. Okay. So there's no intuition which carries over. I mean, this intuition doesn't carry over from Newtonian gravity. Okay, we'll also look at other cases of symmetric solutions. So we look at spherically symmetric solutions. So we'll see that this describes the metric around a star. Oh, sorry. We'll see that these spherically symmetric metrics describe the metric around a star, and also they can we can extrapolate these spherically symmetric metrics, okay, to get what are called black hole solutions. So these are entirely new solutions that only show up in general relativity, regions of space-time where the curvature becomes infinite, actually infinite. Okay, so in one sense you can think about that point in space-time is just gone. We don't know what happens there yet. Okay, we don't really have an understanding of what happens at these curvature singularities, but around it you form something called an event horizon. Okay, very similar to a Rindler horizon. If you're outside the event horizon, you have no idea what goes on behind it. So just like the Rindler observers, you have no idea what is happening beyond the Rindler horizon. Nothing there can actually communicate with you. We are like those Rindler observers sitting outside a black hole. Okay, if you don't fall into the black hole, there's no way to tell that what is happening inside the black hole. So that singularity is sort of hidden away from us. Okay, so this is something quite interesting that we'll discuss extensively at a later point. The other thing is, by looking at very symmetric stress energy tensors, we can simplify our solution to Einstein's equation. So we look at spatially homogeneous or isotropic sources, and we'll solve for, let's say, matter with constant density. Everywhere in space it's constant, or radiation with everywhere in space a constant radiation density. This will also have some kind of pressure. Okay. And these kind of solutions will be very relevant for understanding cosmology or the expansion of the universe. Okay, so we'll study these kind of solutions as well. And even though our equations, the original equations are coordinate system independent, once you have a particular source, okay, the symmetries of that source make it convenient to solve using a particular coordinate system, right? Just like if I have a point source in Newtonian mechanics or a spherically symmetric source, it's convenient to use spherical polar coordinates, right? Similarly, solving Einstein's equations will be convenient if you choose a coordinate system which is in line with the symmetries of the source that you have. Okay. Now, even though the exact solutions cannot be superposed, exact solutions are still very powerful, okay, even for these nonlinear differential equations. Because once you have any exact solution, you can perturb around these exact solutions to find approximate solutions, okay? So anytime you have an exact solution, so even though we have very few cases, these spherically symmetric solutions, these homogeneous solutions, these vacuum solutions, very few cases where Einstein's equations can be solved exactly. Those exact solutions are powerful because any real world situation, you try to map to some approximation around these solutions, okay? This fails, for example, in the region Malvika asked in the beginning of the class, which is if you have two binary black holes going around each other, it's not approximately like a single black hole, right? And we don't have an exact solution there which you can perturb around. Okay. But maybe you can perturb, let's say, in the limit that one black hole mass is much smaller than the other black hole mass. So in an expansion of the mass of the smaller black hole by the mass of the bigger black hole, you can still think of it as approximately a solution generated by a single black hole of mass m, okay, and corrections to this of order m by m to the metric, okay. So there's still some perturbative things that you can do. Obviously, when both black holes are of similar masses, then your approximations break down. Okay. So for each type of solution, okay, not only do you want to find the metric, now you want to go back and look at what happens to particles in this metric, okay, which are moving in this space-time. So you'd like to find the geodesic equation to find the motion of a test particle in such a background. Okay, so that is, supposing we find that there is some correction to the metric, which is phi or some h mu nu. What effect does this have on test particles? So as we'll see, when you take these corrections to the flat space metric plus some corrections involving a scalar field, okay, something like this. When you take into account these type of corrections, what we'll find is that these solutions phi are exactly like solutions to Poisson's equation. Okay, at least in some approximation, they're solutions to Poisson's equation. So it's exactly like solving for the Newtonian gravitational potential. And when you solve for this phi, okay, due to some heavy point source like the sun, okay, now you find the test motion of trajectories of, let's say, something like the Earth in this metric. Okay, and what you'll find is the motion of the Earth around in this background space-time, okay, will be exactly like what you would have expected for something moving in the gravitational potential of the sun in Newtonian mechanics. Okay, so even though it's really inertial motion, that is, its particles are moving along geodesics. They're moving along geodesics in a curved space-time. The metric is not flat; it has curvature because of these extra terms. That extra curvature causes the geodesics to warp. They sort of start coming together. So the motion of the Earth in this curved space-time seems to us, in the coordinate system that we use, it seems to us like circular motion around the sun. Okay, but that's really straight line motion in a curved space-time. Okay, so the motion of the Earth is a straight line in curved space-time. And this definition of straight means straight in this full manifold of space-time. Okay, it's the shortest. It extremizes the proper time. Okay, that appears to us in the coordinate system that we're using as circular motion. Okay, but that's really a straight line motion in curved space-time, because of course you have to think about the motion in time, right? So in x versus t, right, the motion of the Earth is approximately something like this, right? Okay, this is a straight line in a curved space-time. Okay, we'll see that exactly the effect of the metric of the sun causes the curvature of space-time in such a way that the geodesics in that curved space-time look exactly like this. Okay, but again, this is only true in perturbation theory. The corrections ensure that the orbit of the Earth will not exactly be circular, not even elliptical. The ellipses will precess. Okay, so I think that's a good stopping point for today. So what we're going to do in the next few classes is basically just work through these points that I've written out today. So what I've given you is a roadmap for the next few classes. Okay, in fact, probably till the end of the semester. Okay, so what we're going to do is we're going to start with, in the next class, we'll try to understand, we'll start way back here with this roadmap. We'll try to intuitively understand what the stress energy tensor is in the next class. Okay. Okay, I'll pause for any questions and then we'll stop. Yeah. Oh, okay. A constant gravitational field is different from a constant source. A constant source means at every point in space-time, there is a source of vacuum energy, and it's the same vacuum energy. Okay. A constant gravitational field on the other hand, as we've seen, is fictitious. Okay, and it can be, it's basically corresponds to flat space-time where I'm in non-flat, non-Cartesian coordinates. No, that's not right either. Yeah. So T mu. So basically, you have to be a little clear what you mean by that. This stress energy tensor T is not a constant. It's proportional. That vacuum energy solution was proportional to G mu. It is the prefactor of that which was the constant. Okay. So it's not that T mu was a constant. I mean, what do you mean by a constant tensor, right? It's not a constant tensor. It's proportional to G mu. Okay, any other questions online? Yeah, Anisha has a question.
Yes, sir. So, I mean, just by Occam's razor, we would expect a simpler theory to be true. So, unless there's evidence against it, so what is sort of the evidence against the linearized version of gravity that we said was compatible with special relativity?
Yeah, okay, that's a good question. So, Anisha's question is, using the Occam's razor principle, right? You would take the simplest correction, so to be the right theory. Okay, that is, why can't we just use linearized corrections to gravity and say that that is the exact theory? Okay, at linear order. Now it turns out that the predictions of general relativity, the prediction of black holes, the predictions of an expanding universe, all these predictions can only be seen in the nonlinear theory. You can't see them at linear order. Okay, and those have been beautifully tested. In some cases, the experimental evidence came first, like the precession of the perihelion of Mercury. That is something that was empirically observed, but it only tests these corrections to linear order. Okay, but the full nonlinearities, you can already see them. You can only get these exotic solutions like black holes, expansion of the universe. You can only get them in the full nonlinear theory. You cannot get them in this, and we have experimental evidence of the existence of black holes. We have empirical evidence for the expansion of the universe. Okay, so all of these ideas are very beautifully tested.
Yes, sir.
By the way, there are other nonlinear corrections that you can have to Einstein's equations themselves. Okay, and this particular combination that we have taken is one possible solution, but you can have these higher order corrections to Einstein's equations. Those are called modified gravity theories. We don't yet, so already Einstein gravity is the Occam's razor solution if you assume coordinate invariance. But if you assume coordinate invariance, you can still have corrections to Einstein's equation, which are sort of even more nonlinear. Okay, those and they involve higher number of derivatives, like fourth order derivatives of the metric and so on. Those we have not considered. Okay, I think this is a good point to stop. So thank you all. And yeah, we'll stop it. We may not have class on Monday. Okay, I'll let you know. If we don't have class on Monday, we'll have to make it up at some later point.